evaluate the following limits. If I wanted to use those limit laws, okay, the first few that we had, if we had the limits of things being added or subtracted, what can we do? Take the limit of each one individually. Okay, so we're going to kind of show some work here today. You have to write it out, no shorthand, no cheating. So we have the limit as x approaches 5. You have to have that on every term of 2x squared. Minus the limit as x approaches 5 of 3x. Plus the limit as x approaches 5 of 4. Okay, so that's because we have 3 terms, so we can do the limit of each term separately. But we can keep going from here. If we have a constant, so when I have that 2x squared, what can I do with my constant? It can go out in front of the limit. The final thing we had, when we had powers, remember we could move those outside the limit as well. So we could do 2 times limit as x approaches 5 of x, and then square that. Minus, we can pull out the 3, so we have 3 times the limit as x approaches 5 of x, plus the limit as x approaches 5 of 4. Okay, it's kind of annoying, but we are one step from the answer. Because we had a rule Friday that said if you have the limit as x approaches a number of x, it's just that number. So this turns into 2. The limit as x approaches 5 of x is now just a 5 squared. Minus 3. Limit as x approaches 5 of x is just 5. Plus, the limit as x approaches 5 of 4. The limit as x approaches a number of a constant is the constant. Okay, another way to think about that. If my function is just 4, that's a horizontal line at 4. So no matter where you are on that line, isn't your y value always going to 4? Yeah, it's just a flat line. So this limit is just equal to 4. Now we can just evaluate this. So this is 50 minus 15 plus 4. And we get 39. Okay, so a little bit of writing, but isn't that faster than making all those t-charts and plugging in numbers and seeing what happens? Yeah. All right, B. What do we do if we have the limit of a fraction? The limit of the top divided by the limit of the bottom. And then we can break it apart just like we did these. So we do the limit of each term. So the x cubed, we could do the limit of x and then cube it. This would be a 2 times the limit as x approaches -2 of x, and then we would have to square it. Minus limit as x approaches -2 of 1. Minus, on the bottom we have the limit as x approaches -2 of 5. Minus 3 times limit as x approaches -2 of x. Okay, so I did the limit of each term, pulling coefficients out, and moving the exponents out. Now, when it says in the directions that I had to justify my answers, you have to show this work. So we just wrote the limit a ton of times right there. Now, we should be able to evaluate this using those same two properties. So the limit as x approaches negative 2 of x is going to be what? Negative 2 cubed. Plus 2 times the limit as x approaches negative 2 of x is negative 2. And that was squared. Minus, what's the limit as x approaches negative 2 of 1? What's the limit as x approaches negative 2 of 5? 5, because it's constant. Minus 3 times the limit as x approaches negative 2 of x, which is negative 2. We get negative 111. Yes.
Aren't you essentially just dropping the limit and plugging in whatever x approaches?
Okay. So that's what the rule tells us, is if you can get it down to the limit as x approaches something of x, that is just the number you're approaching. So yes, that's what we're doing. We're getting it down to the point where it looks like the property, and then that limit is just equal to the number. Okay, so essentially, on both of these problems, all I really did was plug in my number, right? Now, we know a little bit about limits, and we know that a limit isn't what happens at the number, it's as we're approaching. So sometimes, isn't it possible that when I plug in the number, I might get one answer, but if I looked at the graph or the tables, I would get something different? Because we can have open circles and closed circles. So it'd be really nice to know when I can just plug in and when I have to do something else. This is faster than making tables, but it's still a little tedious writing the limit over and over again. But we have this lovely property called the direct substitution property. And it tells us, as long as we have a polynomial or a rational function, so polynomial, nice integer exponents, or whole number exponents, I should say. Rational function is when you're dividing polynomials. As long as a is in the domain, then you don't have to write out and use the whole limit laws. We can just plug it in. So basically, as long as you are able to plug it in and it doesn't give you a divided by 0 or something like that, we can just plug it in from now on. We don't have to make tables or look at the graph or even write out all those limit laws like we did on the previous examples. So we've kind of been narrowing it down and getting a shortcut out of it. So it's saying I could now go back to this. Isn't this just a polynomial? Yeah. And so now if I gave you that on a test or quiz, you could just recognize, oh, that's a polynomial. All I have to do is plug in my 5. And that would be my answer. Okay. This one, it's a rational function. If you plug in -2, does the bottom give you 0? No. So then we could just plug in -2 and get the answer. We don't have to write out all the steps like we did. All right, let's look at this one. The limit as x approaches 1 of x squared minus 1 over x minus 1. Can I just plug it in? No. Why? Okay, we get 0 on the bottom. So let's go back to things that we know. Is there any kind of algebra we could do that might help us get rid of that problem? Conjugate is a good option if we have radicals. Look at the top for a second. X squared minus 1. Difference of squares. We reviewed factoring at the beginning of the semester. And we know that would factor into x plus 1, x minus 1. Now, you have to write the limit. You have to put that limit on every single step until we evaluate the limit. If you do not, you are going to lose tons and tons of points. Okay, it is required until we evaluate the limit. It's just like having a square root or a square or something like that. You can't just drop it. Okay, it's there until you evaluate it. What happens now? So now I have a limit as x approaches 1 of x plus 1. Now isn't that just a polynomial? And then we can plug it in. 1 plus 1 is 2. Okay, so if we'd made those tables or looked at a graph, we would have gotten the same answer. We just did it a lot faster now using limit laws. So today our focus is really going to be what kind of algebra can I do to simplify this to get to the point where I can just plug in my number. And this is just telling you if two functions are equal except at a single point, their limits are the same. Now, if you graph x plus 1, it's slightly different than this. This is a line with an open circle in the middle, but limit-wise, they're the same because we don't care what happens at that particular point. All right, let's look at this one. The limit as x approaches 1 of g of x. But g of x is a piecewise function. Now, I haven't really given you any rules for piecewise functions, but if we are approaching 1, that means it's not equal to 1. So if you are putting numbers bigger or smaller than 1, which of these two pieces are you on? The first. If you're putting in anything except 1, you're on that first piece, right? So when I'm doing this limit, I don't care what happens at 1, I care everywhere else, so I really only care about this first piece. So what's this limit equal to? And you notice the step where my limit goes away is when I plug in that number. That's when the limit disappears. Yeah, because it's just a point. If you graph this, x plus 1, that's a line, y-intercept of 1, slope 1. But that was for not equal to 1, so that would have actually been an open circle. It's equal to pi when x is 1, so the graph looks like this. So you could see as you are approaching 1, you're on this line the entire time. And we're going to 2. Let's look at this one. First question, always check. Can we just plug in? No. Why? H is 0, and we can't have 0 on the bottom. So if you are getting 0 on the bottom, you cannot plug in. So we have to figure out something we can do to essentially cancel that H off the bottom. What are your thoughts? Well, okay, we need something to cancel out, right? Look at the top of the fraction. What could you begin with there? FOIL. Could we just go ahead and multiply this out and see what happens? Yeah, let's do that. So this is like 3 plus h times 3 plus h. So that would be 9 plus 3h plus 3h, so plus 6h plus h squared. Notice I'm writing my limit because I have not plugged in the 0 yet. What happens now? Yeah, we can do the 9 minus 9. So those would cancel. Okay. Now what can you do? Yeah, we can divide. 6h divided by h is 6. H squared divided by h is h. Can we plug in now? Yes, it's no longer 0. So now I'm plugging it in so the limit goes away. So 6 plus 0 is 6. Can I just plug in? So what could we do? Can I do the square root of each of those terms individually? Okay. It's not a perfect square, just like if I had t plus 9 and a square on the outside, you can't just square each one, you'd have FOIL. So I can't just square root each one. Okay, so I can't really do anything to simplify the top. What strategy can we do with radicals? What's something we've done with radicals before? Conjugate. Okay, good option. On the top I have 2 terms, and I can't really do anything unless that square root is gone. So we can multiply by the conjugate to cancel that square root. So we're going to multiply by the square root of t squared plus 9 plus 3 on top and bottom. No, the conjugate, you're changing the sign in between the radical and the constant, not the sign under the radical. I haven't plugged in 0, so I'm still writing my limit. So on the top we FOIL. When I take the square root of t squared plus 9 times the square root of t squared plus 9, what happens? They're conjugates, so the outside and the inside cancel. Negative 3 times 3 is negative 9. On the bottom, I am not going to distribute because my goal, I have to get rid of that t squared on the bottom so that I can plug in my 0. So it's going to be easier to cancel it if I leave it in factored form. What happens here? We're trying to simplify. What do you notice? The 9's cancel. That leaves me with a t squared on top over t squared times the square root of t squared plus 9 plus 3. Now what happens? So that's a 1 over square root of t squared plus 9 plus 3. Can I plug in my 0 now? Yes. So now my limit goes away. So we have 1 over the square root. 0 squared plus 9 is 9. Square root of 9 is 3. 3 plus 3 is 6. So I get a 1/6. Much faster than making a table of values or anything. Any questions so far? So we kind of looked at some of our strategies. We've used factoring and reducing, multiplying things out, multiplying by a conjugate. So we've used all those different options. Alright, this is something we've already talked about. The limit, overall limit, only exists if the left and right hand limits go to the same thing. So we know to have a two-sided limit, both one-sided limits have to be equal to one another. Alright, so let's show that the limit as x approaches 0 of the absolute value of x equals 0. We do not have any limit laws concerning absolute values. In calculus, anytime we have an absolute value, we are going to have to rewrite it as a piecewise, and I think we've already done this a time or two. So what does absolute value do? Okay, so if you put in a positive number, it doesn't change anything. So it's just x if x is greater than or equal to 0. But if you put in a negative, so if you put in a number less than 0, it does the opposite. It makes it a positive. Okay, we know, what's the graph of an absolute value look like? A V. Okay, so we know it's kind of like this. The negatives, x values still have a positive y value. So if I'm trying to look at the two-sided limit, I would have to look at each. Let's look at the left and right. If you're approaching 0 from the right, that means from the positive, things bigger than 0. Are you on the first piece or the second piece? The first. So this is the limit as x approaches 0 from the right of x. So we know we can just plug that in. Left and right, so even though it's 0 from the right, you're still just plugging in the 0. Okay. If you are approaching from the left, we have things smaller than x. So we have or smaller than 0. So we have the negatives. So this is the negative x section that we're on. But if we put in 0, what is the opposite of 0? Still 0. So the left hand, right hand limits match. That means the overall limit is the same. Now, that probably would have been pretty easy. We could have just looked at the graph and got it, but I'm trying to show you our strategy. Anytime we're dealing with absolute values, we are actually going to break it up and do the left and right hand limits and try to compare those two. I think I want to stop here for today. So, homework. I'm going to give you guys a chance to practice. I have posted a handout on Google Classroom. It is 8 questions. You need to be showing work like I did on these. So a lot of times you might just be able to plug things in, but make sure you're writing your limit up until that step where you plug in.